All right, guys, this is Unit 3, the last piece of the unit called bond hybridization, okay? So we're going to run through, now that we have a little bit of an idea of three-dimensional shape, we're going to really understand why, okay? So we're going to take the first example here. This is just very simple, and this is methane, right, CH4. So Lewis structure is this, right? And in terms of three-dimensional shape, this one is going to be tetrahedral, okay? Because it has 4 bonding areas and 0 non-bonding areas. And that's going to give this a tetrahedron shape. In other words, it looks like a 4-sided figure, kind of. Right? So it's not flat on the page like our drawing is. It's more like the picture over here. And what we also know is that when you have a tetrahedral shape, you have very predictable angles. In other words, all of these angles are going to be about 109.5 degrees. And they're all going to be equal distant, right? So this angle, that, etc. They're all going to be the same. And you can measure that in mole view, which you guys are probably figuring out about in your lab activities, okay? So the question is why? Why are these all equal and so on? And how do these things actually bond, right? We know that they're sharing electrons. But if electrons exist in orbitals, like s or p orbitals, how do they actually share, right? Well, what ends up happening is the bonds actually overlap, the orbitals actually overlap and increase the space that the electrons can be, okay? So if this is the hydrogen here, if I just put H's here, right? And then the black is the carbon in the middle, what must happen for each of these connections here is that an orbital of the hydrogen must overlap with an orbital of the carbon. And then there'll be 2 electrons that will share that space, right? So let's take a look at what that looks like. If we draw these quick little orbital diagrams for each of the atoms, right? So hydrogen, it just has a 1s box, right? That's it. And it only has 1 electron in that. So we'll put it like that, right? And obviously there's 4 of them, but for now, let's just keep it like that. Carbon, if we just take the valence, is going to have 2s and 2p. And we would draw it out like this. And carbon has a valence of 4, so it would look like that. So hopefully you're with me so far. Okay, so how do we get methane out of this? If you look at the carbon right here, right now, it looks like it only has 3 available orbitals to bond with because this 2s is already filled up. So I have a space here where I can overlap, I have a space here where I can overlap, but then I have an empty orbital here, so I would need to put 2 electrons in there, right? And so the way this would work in theory, right, is I would have 1 hydrogen 1s overlap with this one, another hydrogen 1s overlap with this one, another one, I guess, overlap with this one, but then what about that 4th hydrogen, right? Where's it going to overlap with? Because it can't overlap twice with the same orbital, right? So it doesn't work. And the other way we can back this up is to see that each one of these angles that we've measured is exactly the same, okay? So if this strictly overlapped the way it appears kind of right now, I would not have 4 equal bonds, right? Because one of these would have to overlap somewhere else, okay? Or one of these would look weird, and it doesn't. They look all the same. So the other theory then is that when it bonds, carbon actually becomes kind of excited. So this is not what happens. So what ends up happening is carbon rearranges just a little bit. And yes, this takes energy. However, the reduction in energy that you're going to get from bonding is going to overcome this. So by doing this, okay, we've now created 4, right? 1, 2, 3, 4 overlapping bonding sites for those hydrogen 1s orbitals. Now, this is what we thought for a long time. However, again, going back to our data up here, right? If it did this way, remember the difference between the shapes here. An s orbital is a sphere, and a p orbital is the dumbbells, right? So we have sort of the x, the y, and the z of the p orbitals. Very different shapes. So if I know that my hydrogen is going to overlap with each of these, p orbitals give one shape, s orbitals give another. So I should have, right, like one of these would not look like the other 3, if that kind of makes sense, right? One would be an s to s overlap, sphere to sphere, and the others would be sphere to dumbbell, and they would all look the same. But again, we know that's not true, okay? The data shows us that all of these bonds are exactly the same. Same distance, same angle, everything. So this is where the hybridization theory comes into play. Okay? Hybrid, meaning a cross between the two. So let me just move this picture down just a little bit. Don't freak out about that yet. Okay? So what we see happen is that carbon actually hybridizes all of its orbitals. So it takes these 4, right? Notice the 2p are slightly higher energy than the 2s. So what carbon actually does is not this again, and it actually creates 4 equal orbitals that are a hybrid of the s and the 3p. Okay? And they're in the middle of the energy levels here. So actually, maybe I'll draw it up here so you can see better. Let's do that. So they would be like this in terms of the level, right? Higher than S, lower than P. So they hybridize them. And what do we call these new formed orbitals? Well, it depends on what you've hybridized. Here we've hybridized 1s and 3p orbitals. So guess what we call this? S, P. 3 hybridized orbitals. And they're all the same. Okay? So how does this work? Well, now we have sp3 orbitals that are now a combination of the shapes here. So it's not a defined sphere or a defined dumbbell. They're all the same. It's sort of like a half sphere, half dumbbell sort of shape, right? So they all sort of have like a figure 8, but it's smaller. Okay? So how does this look when they're drawn? So if we have our carbon in the center, it now has, and the little loops are on the inside, so I'll just draw the bigger loops. So carbon now has 4 equal sp3 orbitals that each have an electron in them. Right? So what happens? So all the hydrogens come in, and remember hydrogen has an s orbital, and overlap. So hydrogen overlaps there, hydrogen overlaps here, here, and here. And those other electrons come in and bond. And that's why we get 4 equal distance, equal shape, equal angle bonds. That's the theory, the hybridization theory. Okay? This doesn't just happen with things bonding, meaning this would happen if we had non-bonding as well. And so an example of that would be NH3. So NH3 looks like this. It behaves, and I think you guys are realizing this in your lab, it behaves as if it were like methane because it has this lone pair of electrons that plays a role, that takes up the space just like a bond would. And so we end up with still 4 zones of electrons And we see, again, sort of equal distance, equal bonds, and so on. And so the thought is this would also hybridize. It's just that one of its hybrid orbitals would have 2 electrons of its own, right? So if we were to sort of draw this like we drew the carbon over here, right, we would draw the nitrogen with its 4 new hybrid orbitals, right? And then it would have 1 of its own, 1 of its own, 1 of its own, 2 of its own. And then the hydrogens would come in, overlap, and put their other electron in, like that. We get the same shape, okay? So this is called sp3 hybridization, and that's when you have 4 zones of electrons around the central atom. So if you have 4 zones, you need 4 hybrid orbitals, therefore sp3. Okay, so this is sp3 hybridization. This is another picture here in case you want to check it out, right? So if we're looking at this, we have, this is carbon right here. It has its s orbital here, and then it has px, py, pz here. Those all kind of smush together and make 4 new hybrid orbitals, all kind of angling at a different way, kind of equal pushing away from each other. And you get this tetrahedron kind of diagram here, right? Okay. Okay, so what happens then if you have a double bond in there somewhere? Okay, so let's look at another one here. Let me move this down. So we're going to draw something called ethene. Now this is starting to become an organic molecule because it's carbon-based. And so this is an organic naming system that we may or may not get to towards the end of the year. And the way this works, okay, we haven't done kind of larger molecules here, but carbon has to go kind of in the middle. But you kind of have to put both carbons in the middle because the hydrogens can't. And so we end up with each carbon has 2 hydrogens. And they're connected, but they need to actually have a double bond in between them because there's not enough electrons to make it work. So there's a double bond here. So how do we talk about shape of this, right? Like 3-dimensional shape. Well, you kind of have 2 central atoms. So the first central atom, we'll call this carbon 1, we'll call this carbon 2. The first carbon has 3 zones of electrons around it. 3 zones. So that's going to spread out into a trigonal planar shape. So this is actually going to be planar, flat. Now look around carbon 2. This one also has 3 zones of electrons. So it's also going to be planar around that carbon, which means if they're both planar, they're going to be planar together, which means this whole thing is going to be planar or flat. Okay, so how does this bond? Similar setup, right? Except it only has 3 things connected. So it only needs to hybridize 3 orbitals, right? And so what it does is if we kind of take our normal carbon, which is the 2s and the 2p, right? Normal carbon with our 4, okay? It's only going to hybridize 3. Now you might say, well, why doesn't it just use the 3p orbitals, right? They're all the same. Yes, however, remember that hybrid orbitals are sort of in this in-between energy. So they're slightly lower energy than 2p, and they're slightly higher than 2s. And so it actually does make sense for this thing to hybridize. But it only needs to hybridize 3. So what does it do? So it takes this, and it turns it into, try to do this at the right height here so we can see the energy difference. These guys, and then that leaves an extra 2p orbital over here. So what are we going to call these 3 new hybrids? Well, I took the s and I took 2 p's. So these are going to be s Oops, that's not an S. sp2. One s and two p orbitals smushed together. And I'm going to do the same thing. I'm going to spread out my electrons here. Okay? So now what this does is it gives the carbon 3 equal orbitals to do its bonding with, its primary bonding. And then it has this extra p orbital that it can start to think about double bonding with. And that's where the double bond comes in. So how does this work? Well, just like before. So we're going to take this carbon on this side. And now it's going to have its 3 hybridized orbitals. Right? It only has 3. This carbon over here, it's going to have its 3. Oops, sorry. Drew that a little bit wrong. It's going to have its 3 hybridized orbitals. Okay? Remember, each of those are going to have their 1 electron. And then here we'd already have 2 because each guy's bringing 1 in there. Okay? Then we have our hydrogens, which are going to bring their 1s orbitals over. Right? The spheres. Okay? And that's what we have, at least in terms of the skeleton structure. Now, what we know is that we have a double bond between the carbons. So where does that double bond come from? Well, remember, it's carbon to carbon. And so one of the carbons, as we just drew up here, has this extra p orbital. So the other carbon also has an extra p orbital. And if they're lined up, right, so in theory, this carbon still has an extra p orbital here, and this carbon also has an extra p orbital here. What we see happen is that these p orbitals just kind of bend together, right? They kind of squeeze in and overlap, okay? And you end up with sort of a little bit on top, a little bit on the bottom. It almost, if you're drawing it, it almost kind of looks like a triple bond, but it's not, because the p orbitals here, they're all part of the same orbital, okay? And so they just kind of overlap here and overlap here to conjoin and make one big orbital, right? So if this guy has 1 in here, and he has 1 in here, they can overlap and make that extra bond. So what we want to get at here, right, is in our structure, one of these double bonds is not like all the other bonds, okay? Because it's not a hybrid orbital. It's an overlapping extra p orbital, right? And so what we do is we call these things different things. All bonding overlapped orbitals are called sigma bonds. That's the symbol for sigma. They're called sigma bonds. Those are the actual bonds, right? The bonds that are overlapping the different atoms. Okay? We call the extra overlapping p orbitals, we call them pi bonds. So these are sigma bonds. These are pi bonds. Okay? So if I was looking at this molecule, I would say, if I'm counting bonds here, I would say I have 1, 2, 3, 4, 5 sigma bonds, right? In other words, wherever the atoms are connected, that's a sigma bond. And then I have a double bond here, so I would have 1 pi bond. If you had a triple bond, you would say we had 2 pi bonds. We'd have another pi bond. Now, if my drawings are not the best, you can maybe look at this guy right here. Okay? Same kind of thing. You have the carbons here overlapping with their sp2, and then the pi bond is overlapping on the top. So we call this sp2 hybridized, because there's only 3 things connected, 3 substituents, and so that's going to be sp2 hybridized. Okay? Last one we'll look at quickly, CO2. okay? Which if we draw the Lewis structure, which I hope you're starting to understand, we always want to do Lewis structure first, okay? Notice here we only have 1, 2 zones of electrons. They're going to be super far apart, making this a linear structure. So because I only have 2 things connected, I only have to have 2 hybrid orbitals, right? I only have to have 2 hybrid orbitals. The other 2, this one over here and this one over here, are going to be a result of the overlapping pi bonds from the oxygen. Okay? So remember, oxygen has a valence of 6. So 1, 2, 3, 4, 5, 6. So looking at oxygen, it has 2 options for where to bond, right? It has 2 p orbitals. It's going to use 1 to overlap with the carbons. So here's carbon, and it's going to have now 2 hybrid orbitals that are together, right? With 1 electron each. Okay, and then it's going to overlap here with our oxygen. So our oxygen is going to have a p orbital here, right, that it's going to overlap with. So we'll have an oxygen over here with a p orbital here that it's going to overlap with, because right, it doesn't, its s is full, unlike a hydrogen. Then it's going to use its other extra bonding spot, right, this extra p orbital here, to overlap with the extra carbon p orbitals, right, that has 2 now. And we'll talk about the shape of this a little later on. So this one's going to overlap here. This one's going to overlap here. And so we end up with, if we're counting sigma pi bonds, we have the connection between the C to the O here, connection between the C to the O here, so 2 sigma bonds. Then we have the extra double bond here, the extra double bond here. We have 2 pi bonds. And we're going to talk about this shape a little bit later on, but that gives you an idea. So CO2, the carbon only has 2 things connected to it. Therefore, it only hybridized 2, right here and right here. It only hybridized those 2 orbitals of itself. So this is just called sp, right? 1s, 1p smushed together. Okay? So if I ask you, what's the hybridization of an atom, like a central atom in a molecule, you can draw out the orbital diagrams and figure it out. Or you can start to understand by counting substituents, right? Counting areas of electrons and figuring out how many of them would have to be hybridized. And you can call it, so it's usually sp3, sp2, or sp. It is possible to have a hybridized d orbital, but it starts getting a little messy at that point, so we're going to focus primarily on these. Okay? Hopefully that's starting to make sense, and we'll talk a whole heck of a lot more about it in class next time. Okay?